So because of that, those pores, right, having gas inside them, it will expand when it is subjected to heat, right? So that will cause micro cracks, right? So that comes off as a disadvantage, you can say, in die casting. Was that clear? Cold chamber die casting. Any doubts you can ask? Now you see hot chamber die casting. As we know, die casting process is the use of high pressure, right, to force the molten metal through a mold called a die, right? You see here, many of the superior qualities of castings manufactured by die casting can be attributed to the use of pressure to ensure the flow of metal through the die, right? With the help of pressure, you are trying to ensure the flow of metal, right, as is required. Now you see, hot chamber die casting, the supply of molten metal is attached to the die casting machine and is an integral part of the casting apparatus for this manufacturing operation. Unlike your cold die casting, you see here in hot chamber die casting, this setup, okay, for the molten metal, right, is submerged, as you can see, right? This molten metal will be the formation of this molten metal or the supply of molten metal will be an integral part of the process. Okay, that's what makes this different. What is the difference? If someone asks you what is the difference between hot chamber die casting and cold chamber die casting, it is based on this point. Okay, this is the point that differentiates that the supply of molten metal is integral to the casting apparatus, right? In hot chamber die casting, unlike cold chamber die casting, wherein it will be this molten metal which will be filled here, okay, should be filled from here, is melted somewhere else, right? It is not part of the apparatus, this casting apparatus. Unlike hot chamber die casting, you are having the facility, the supply of molten metal is integral to this casting apparatus. Okay, that's what makes this different. So this is basically your temperature that you are trying to achieve and the time that is required, because you see, if that molten metal was melted at some place else, right, and while traveling it would have had some oxidation or slag, reduction of temperature, right? So all that can be avoided when you have hot chamber die casting, right? Right. So the pressure exerted on the liquid metal to fill the die in hot chamber die casting manufacture usually varies from 700 psi to 5000. If you are talking about MPS, 5 megapascal to 35 megapascal. That is the pressure range that we can work in. Pressure is held long enough for the casting to solidify, right? So unless it solidifies, that pressure will not be removed. So the pressure is held long enough. You see here, that is your setup for hot chamber die casting. Very similar to the previous one, cold chamber die casting, but as I was mentioning, this molten metal which is applied here, right, is melted here itself in this chamber. So that is where this molten metal gets inside. That's called the intake port, right? And with the help of this plunger rod, we're trying to apply some pressure on this molten metal. It will flow like this. Once the molten metal is inside, you'll close this intake port. Okay, so when the plunger increases the pressure or tries to come down, the molten metal has no way to go except to that mold cavity, right? Or this mold, simply speaking. So that this plunger is responsible for creating that pressure for that molder metal to go inside this mold cavity. As simple. Okay. You see, hot chamber die casting has the advantage of a very high rate of productivity, right? Because no time is lost, isn't it? It is melted here itself and you're trying to push it. So a very high rate of productivity during industrial manufacture by this process. One of the disadvantages is that setup requires that critical parts of the mechanical apparatus, that is the plunger, must be continuously submerged in molten material, isn't it? This plunger is in continuous contact with this molten metal, right? So it has to be of certain material that it can withstand the properties to be able to function for long, right? So that comes off as a disadvantage, that those critical parts are in continuous contact, right, with the molten metal. Continuous submersion at a high enough temperature material will cause thermal related damage, isn't it? Not just expansion because of the temperature increase, but damage because of prolonged temperature, prolonged what do you call it? That it stays at that temperature for a long time, right? So causes that damage, right, rendering them inoperative. So that affects their service life. For this reason, usually only lower melting point alloys of lead, tin, and zinc are used to manufacture metal castings with the hot chamber die casting process. Okay, so the hot chamber die casting, these three are used because they are having a lower melting point, right? So that will not affect the plunger material a lot. Is that clear? Die casting, hot chamber and cold chamber die casting. Okay, so you see, I've put this slide just so you can understand uh, what are the different processes that we have seen and the advantages, disadvantages in the example components, right, that can be made. So when it comes to sand casting, right, so let us start from the bottom, right, that what we have seen last is die casting. So die casting, you see advantages, excellent dimensional accuracy, high production rate as we have discussed. Disadvantages, costly dies, right, as I told you. To be able to manufacture those dies, the R&D and etc. will cost you a lot. Costly dies, small parts can be made, right? Not bigger parts, very small parts or medium components, you can say, relatively medium. Non-ferrous metals, right? Because of the fact that higher temperature materials would require, I mean, the plunger would be staying in contact with them, right? So that's what the reason that we have discussed just now in the last slide. Example components that can be made: gears, camera bodies, and car wheels, right? Before that, what we saw was centrifugal casting. So centrifugal casting, the advantages are large cylindrical parts can be made of quite a good quality, right? Because of that directional crystal structure. The disadvantages, it is expensive and only few shapes can be made, right? Because of the fact that we are utilizing centrifugal force. So relatively cylindrical components can be made. So that comes off as a disadvantage. Pipes, boilers, and flywheels. These are the general components that are made with centrifugal casting. Before that, we have seen investment casting. Advantages that it offers: complex shapes can be made, excellent finish can be achieved. Disadvantages: only small parts can be made, right? As I said, jewelries are quite useful application of investment casting. If not for that, you have turbine blades, but relatively small parts can be made, and they are expensive, right? Because it requires a lot of steps, time, and effort, right? So that is what makes it expensive, even for the mold, right? To be able to make that wax pattern, you have to have a mold, and the mold will cost you. Examples, as I said, jewelry, right? And even this thermal turbines, right? Thermal turbine blades. So aerospace industry also uses it a lot, and the boiler industry for production of those blades, right? Impellers and blades. Before that, we have seen shell mold casting. Advantages: it offers better accuracy, finish, higher production rate. But the disadvantage is limited part size can be made, right? And example components: connecting rods, gear housings, etc. And the first one, what we saw, sand casting. Advantage is that many metals can be used, right? Can be cast of different sizes, shapes, and it is cheap, right? Because of the fact that sand is readily available, right? Certain type of sands are readily available, so that makes it cheap. And disadvantages: the poor finish and tolerance, right? As we have discussed, it requires post processing or what do you call it? Secondary machining after this primary forming in sand casting. So that's why you have this as a disadvantage, that the poor surface finish and tolerance, what do you call it? A lesser tolerance control, right, over the dimension. Example components: engine blocks, cylinder heads, etc. Right? Quite big components, you can say, when it comes to sand casting. Right? Is that clear? Or doubts in this slide? Right? You see, now that ends your special casting processes. Okay? We can expect one of them in the exam, right? When it comes to exam. You see, now the next topic is the design of gating system. Okay? The gating system and what do you call all the components that you have there, riser, etc. Different types of gates we'll see. And riser design. What are the guidelines for designing riser in the gating system, right? So we can have sound casting, right, without any defects and within a lesser amount of time. So as we know, this all counts as gating system, right? Right from your pouring basin, right, where the metal is poured, pouring basin, your screw base, your runner, and your gates, and even riser counts as heating system, right? All that trying to, which is helping us, right, to fill up this mold cavity, right, so that we can have the casting. So all these are, they count as gating system. What are the parts of gating system? The first one being pouring basin, right? We have discussed this in sand mold casting, but let us have them again. It is a conical hollow element or tapered hollow vertical portion, right? The gating system, which helps to feed the molten metal. That's what it means. That's what the aim is, right? Or the objective is for the pouring basin. It helps to feed the molten metal initially through the path of gating system to the mold cavity, right? Next component is sprue, right? As I said, it is not straight but inclined. Vertical passage made generally in a cope using tapered, right? It is tapered, using tapered screw pin connected at bottom of pouring base, right? As you can see, it's connected at the bottom of the pouring base, this screw. and it is tapered with its bigger end to receive the molten metal. The smaller end is connected to the runner, right? So it receives the molten metal and then supplies it to the runner. It has to feed molten metal without turbulence to the runner, which in turn reaches the mold cavity through gate, right? So that's what the aim is for keeping the screw. That trapezoidal cross section is that the molten metal should be fed without turbulence, right? It should be as smooth as possible so that we can have sound casting instead of having entrapment of air, etc. Right? If it is without turbulence, then only it is we can ensure that only molten metal is flowing inside and not the air along with it. Right? So without turbulence, it should be able to supply the molten metal from the pouring base into the runner. That's what the objective of screw is. Right? Which in turn reaches the mold cavity through gate. Okay. Through the runner, right? Through the gate to the mold cavity. Okay, then so we'll see these components in the next class, hopefully. Okay. So if you have seen the guidelines of gating system and riser system, then we can say that concludes your first unit. Okay. Once you have seen this gating system and the different guidelines that we have, that we can have a good casting, a sound casting, the design of the gating system, design of the riser, etc. Okay. Any doubts in today's class? You can ask, or we'll end the meeting. Okay, then. So we'll end the meeting. Thank you.